I'd like to talk about two quite different topics. The first one is on metrology, and the second one is on the work that we did at the Technical University of Munich on describing quantum systems using their phase-space representations. And I'll start with the first topic. So just to introduce the basics of metrology, quantum metrology. So in general, metrology is concerned with estimating or measuring a physical quantity with the best possible precision and estimating this precision from measured data. However, if the measurement device itself is so small or so precise that one has to take into account quantum effects, then there is a fundamental limitation on this precision imposed just by the fact that measurements follow laws of quantum mechanics, and whenever one tries to infer this information about the measured quantity, then one has to perform quantum mechanical measurements, and each measurement destroys the quantum state that contains the information, so one has to repeat the measurement many, many times. And from this, one can derive bounds, what precision one might reach with a given number of measurements. And since this information about the measured quantity is encoded in the quantum state, it's encoded as a quantum information, and that information is very, very sensitive to noise. And that's a problem with quantum metrology. And in this work, we aim to find the best possible quantum states that can do the best quantum metrology. I will focus on variational quantum algorithms, and these are just algorithms for very efficiently exploring the exponentially large state space of qubit systems. And these algorithms are expected to be the first applications of quantum computers. There are a few examples like quantum chemistry methods, which use early quantum computers such as the variational quantum eigensolver, or there are already algorithms for machine learning. But here I will focus only on quantum metrology. Just to introduce the basics, let's assume that we have a qubit state. There are many different platforms, but probably qubit states are the most relevant in this context. Let's assume that we want to measure something like an external field, like a magnetic or electronic field. And this field is then modeled by a Hamiltonian. And the field itself is just a parameter in this Hamiltonian, and we want to estimate this. How do we do that? We start with a probe state that we expose to this environment, to this magnetic field or electric field. And due to this Hamiltonian, this state will evolve into another state, but that evolution depends on the parameter itself. And we want to infer this parameter with the best possible precision. How to do that? We take this quantum state and perform measurements on that. And in quantum mechanics, actually it's not a general form, but just to show you the simplest case, measurement can be thought of as measuring an operator that decomposes into projectors. And after every experiment, the state collapses into one of these eigenstates, so-called eigenstates. And from that, repeating many, many times this experiment, we get these probabilities, how many times the system collapses into a certain eigenstate n, and this probability will depend on the parameter omega itself. And from this, we can estimate the parameter itself using, let's say, a maximum likelihood estimator or some appropriate estimator. But the precision of this system estimation is, or a bound on the precision itself, is determined by the classical Fisher information of this probability distribution. And for example, just to give you an example, if we use a maximum likelihood estimation here, then the maximum, so the likelihood function itself will be a Gaussian, and the sigma parameter of that Gaussian will be related to this classical Fisher information. And simply just repeating the experiment many, many times, one can gain a shrinking sigma of this variance. So in this very, very simple model that I showed you, the optimal states are so-called GHZ states, which take up this form. So they are a superposition of 0, 0, 0, 0 plus 1, 1, 1 states, meaning that all the qubits point to the North Pole, superposed with all the qubits pointing to the South Pole. But this state is very, very sensitive to decoherence. In fact, it's one of the most sensitive states to decoherence. And just to give you an idea how this looks, this is the Wigner function of the GHZ state, and these fringes encode the quantum information from which one can infer this quantity omega. And here now, as time moves forward, under dephasing, these fringes vanish. And in the end, one just ends up with a classical superposition of 0, 0, 0 and 1, 1, 1 without any interference fringes. And we actually optimize for the best possible quantum state that under noise still picks up optimal amount of information. And that state will look like this. As you can see, it's very, very robust against this decoherence. In this paper, we described how to actually find these states using a quantum computer. And let's assume that we start with a parametrized probe state. And this is obtained by putting an encoder circuit after the computation. Let's say we start from a computational 0 state, which is 0, 0, 0, 0. Typically, one assumes that the system starts from that state. And then we apply an encoder circuit to that. And that will create this parametrized probe state, as here. Then we expose this state to the external environment, which now contains both the magnetic field, but also some noise, which we model with some process, quantum process. In the end, we obtain a density matrix, and from that mixed state, we want to figure out what is the parameter itself and what is the precision it encodes. And for that, we use a decoder circuit, then measure in the computational basis, and effectively this decoder circuit just maps the computational basis to another basis, O, for which we can then calculate the previously shown classical Fisher information. This means that we can explore all the possible quantum states and all the possible measurement bases. So we can look for the best possible combination of a measurement strategy and a quantum state. And this setup can be implemented on near-term quantum computers, no matter how noisy they are. And here I show you how this encoder circuit looks like. It just contains standard quantum gates, such as single qubit rotations and controlled 2-qubit rotations or 2-qubit gates. And every gate here has its own parameter, continuous parameter. In this case, we have 80 of these parameters, and we just optimize the parameters themselves to find a sufficient approximation of the best state. And one assumption could be that I showed you here this Hamiltonian. This Hamiltonian is invariant under permutations. So the problem itself has quite strict symmetry. But here, we don't assume any symmetry. Every parameter can be independently tuned, and therefore it's not permutation symmetric. And we numerically simulated this ansatz, and this gives a very, very good approximation of metrologically optimal states in case of many different error models. So we did some numerical simulations to show that this method will work. And we did that the following way. We used Quest, which is a C program that's been developed by our group, and it's very, very efficient for simulating quantum circuits. And it can also do arbitrary Krauss map representations of noise processes. And we explored many different noise models. We assume that the noise itself is continuous in time, so-called infinitesimally divisible, and then it necessarily has this form, such that it contains unitary evolution under the external field, plus some completely positive mapping L, which corresponds to decoherence or noise. But there is no other assumption that needs to be made. And here we actually replace our decoding circuit just by an analysis step, which contains a calculation of the quantum Fisher information. It's a technique that's routinely used, especially in quantum metrology. It's a quantum analog of the classical Fisher information, which at the same time gives us the classical Fisher information of the optimal measurement basis, plus the optimal measurement basis itself. So after obtaining the noisy density matrix, we just calculate this quantum Fisher information, and from that a dimensionless precision, which contains the variance of this estimated parameter, but it is now independent of the decay rate of the noise model. So in some sense, this calculation it depends on the particular choice of noise model, like amplitude damping or dephasing, but it is independent of the rate of decay. And so we then just optimize these parameters and find the best possible quantum states under certain noise models. And we did that up to 9 qubits, and it takes about 2 weeks on a quite advanced computer because the problem itself is very hard. So as I told you, we simulated various different error models up to 9 qubits. Here I show you 2 examples which are very easy to solve, even analytically. One is dephasing, when the noise itself comes from statistical fluctuations of the parameter omega itself. So it's not a fluctuation of the quantum system itself. In some sense, it's a classical noise. So is this, but here we assume that the correlation time is finite. So it's a non-Markovian noise. It's the so-called Ornstein-Uhlenbeck process. And here there are even known analytical solutions in the literature. What's interesting is that the main promise of quantum metrology is that by using G8Z states, one can gain beyond a linear scaling, one can go up to an n-squared scaling as a function of the number of qubits. This is the so-called Heisenberg scaling. But in very early literature, it was already shown that as soon as noise enters the model, the superior scaling goes away, and one cannot do better than with product states, which are shown here. But still, an absolute factor can be gained. So the graphs here show the number of qubits versus this dimensionless precision of estimating the parameter. And the optimal states in case of dephasing are squeeze states, which has been known for a long time. However, if the noise itself is non-Markovian, then one can gain a slight superlinear scaling of this precision. It means that employing more and more qubits, one can gain more and more information about the external field without repeating the experiment the same number of times, or when repeating the experiment the same number of times. But actually, we found something very interesting in case of amplitude damping. So this noise model corresponds to spontaneous emission. This means that there is a finite chance that one of the qubits flips from 1 to 0 and emits a photon. And in this case, it turns out that I show here the ansatz states, which are obtained with this ansatz circuit. They significantly outperform any symmetric state. These are states that are fully permutation symmetric under permuting the qubits. And it also means that there was a previous assumption in quantum metrology that optimal states are invariant under permutations, which comes, of course, from the Hamiltonian. But it turns out under certain noise models, this symmetry is violated. And breaking this symmetry results in a significantly improved performance of these non-symmetric states. So here we even quantify a measure of indistinguishability to quantify on a scale between 0 and 1 how distinguishable these qubits are in the optimal state. And this is defined as just taking the quantum state and permuting 2 qubits, a pair of qubits in that state, and then calculating the fidelity between these 2 resulting states, and then averaging over all possible permutations, pairs of qubits. And as you can see, as the number of qubits increases, the unsat states break permutation symmetry and go to around 0.7, whereas all the other states are fully permutation symmetric, and this measure is 1.0. Just to give you a rough idea how the optimal states look like and why they break symmetry, still the optimal states are very similar to GHZ states, so they are superpositions of 1, 1, 1 and 0, 0. But there is an additional component D, and this D can passively correct for these amplitude damping decay events. And they have this form, so they contain pairs of qubits in state 1, 1, but not in a permutation symmetric way. It's only symmetric when we permute certain pairs of qubits. Yes, and the power of this scheme actually comes from the optimal measurement basis, because that measurement basis can, in the end, decide to which qubit a flip event has occurred, and the additional quantum information comes from that. And of course, there is a symmetric counterpart when it contains all the possible permutations. It's called a decay state, and that actually has lower scaling in terms of the quantum Fisher information. So I showed you how to use quantum algorithm, variational quantum algorithms for quantum metrology. We numerically simulated some noise models, which are most relevant in experiments. And we found something interesting in terms of this symmetry breaking behavior of the problem. And we even derived an analytical model for the case of amplitude damping. And if you have any questions, before I jump to the next topic, please let me know. So was it clear?
Yeah, have you tried modeling symmetric incoherent superpositions? Because I would think that your state could be represented as a classical symmetric superposition of unsymmetric states sort of symmetrized classically afterwards.
So actually the quantum Fisher information always takes its maximum at the boundary of density matrices. So always pure states will saturate the quantum Fisher information. So if I take an incoherent superposition, if I understand it correctly, that it would be a mixed state, a mixture of 2 pure states.
Right, right.
Then it would not be a maximal.
So it's a pure state that's not symmetric.
It's a pure state that's not symmetric under permutations.
Okay.
But it still has quite a lot of structure in it, because if you think, you can think in a way that it's symmetric under permutations of distinct pairs.
Right.
But of course, it breaks bosonic symmetry and.
Interesting.
But the assumption of the field was that bosonic symmetry, or this fully permutation symmetric subspace, is optimal.
And then, but then everything about the noise model and everything is symmetric?
The noise model itself is symmetric, because every qubit receives the same type of noise, same amount of noise. So the entire problem is symmetric.
Very cool.
Anybody else?
Yes?
Is it possible to very quickly say how this computations that took 2 weeks. Probably it's optimization of these 80 gates.
80 parameters.
So is it possible to just quickly give an idea how you optimize in such a great space?
Yes, so it's very slow because the state space is very large. So what we do at this point, we have pure states, which is already exponentially large, but then we apply noise to them. So we have to deal with density matrices. And then let's say we just fix a quantum state and we just want to calculate its corresponding usefulness in quantum metrology, so this quantity. Then we have to first model this process, which is relatively fast. But then we have to calculate the quantum Fisher information, which is significantly slower because it requires one to diagonalize the density matrix. And on top of that, it requires the knowledge of the eigenvectors of the density matrix. From that, we can calculate the quantum Fisher information and this measure. Let's say for 9 qubits, it takes about a few seconds because the state is still not that large. But then we have 80 parameters to vary. And then the question is what method to use for the global optimization, because we are interested in the global maximum to make sure that we actually find something meaningful here. Here it is not even necessary to find the global maximum when comparing to symmetric states, but it was very, very important here to make sure that we certainly find the global maximum, since we claim that this is better than this. And we do that by running many, many optimizations from random starting points and making sure that we arrive at the same solution many, many times. And in the end, it's just a classical optimization problem of a very a continuous surface, but a surface that has many, many local traps. Just to give you an idea why it has many local minima or maxima, is because the quantum Fisher information is symmetric under permutations, because the entire problem is symmetric under permutations. So the number of permutations is proportional or scales with n squared, the number of qubits squared. So we have at least that many local traps. Okay. Okay, then I will probably jump to my next topic. It's on phase-space representations. And this is now a quite different topic. Here our aim is to represent and analyze quantum states using phase-space techniques. And this does not have a direct practical application, although I will mention quite a few practically relevant methods. And I just quickly mention basics of this topic. So you might all know that there are many, many different phase-space techniques for quantum systems. One of them is the Wigner function, and all of them are related to the Wigner function in some way. And in quantum optics, typically the S-parameterized phase spaces are used, such as Q functions or Glauber P functions, and so on. And in time frequency analysis, for example, this Born-Jordan distribution is well known. There are many different applications depending on whether it's quantum mechanics or time frequency analysis. In quantum mechanics, one can use this for tomographically reconstructing quantum states or for efficiently calculating time evolutions of quantum systems. And this is only about flat phase spaces, but it has been shown that these techniques can be generalized to manifolds, so more general symmetries of quantum systems. And I will mainly talk about spherical phase spaces, which correspond to finite-dimensional quantum systems, such as qubits or qubit systems. And one application example here is for flat phase spaces. I plot here the Wigner function. These are typical textbook examples photon states in quantum optics. Let's say it's when the electromagnetic field contains 0 photons, it's a Gaussian distribution. A single photon state or Fock state looks like this. And here it's a superposition, coherent superposition of the two states. Then one can consider the so-called Husimi Q function, which is just a convolution of the previous functions with a Gaussian distribution. It is positive, it has no negative points. And then I plot here the Born-Jordan distribution, which has not been calculated before for quantum mechanical systems. And this is how these states look like in the Born-Jordan representation. And it looks, in some sense, similar, but also there are quite obvious differences. And our aim is to characterize these different variants of the Wigner function. And in this paper, we consider these flat phase spaces. This is the textbook definition of the Wigner function, and it looks very, very complicated. I don't even want to now discuss details of this, because we proposed a much simpler version of this definition, which generalized this to arbitrary phase space representations in the Cohen class. And this Cohen class is actually a generalization of the Wigner function by formally convolving the Wigner function with some distribution or function. This is how it looks. Theta is just an index, which indices what type of representation we are considering. If theta is the delta distribution, then it's the Wigner function. So we define this as an expectation value. The density matrix is here, and it's the expectation value of this operator. And this operator is actually, it contains the so-called parity operator, which we define for the entire Cohen class. For the Wigner function, it's just a coordinate reflection in phase space, hence the name parity operator. And the parameters here are phase space points or phase space coordinates. These can be either characterized by x and p or the complex alpha. In quantum optics, they typically use the complex alpha. And these D operators are so-called displacement operators, which correspond to translational symmetries in phase space. And in the end, the definition of this function just reduces to an expectation value. And just to give you one example, I will discuss now the Born-Jordan parity operator, how it looks and why it's special. This Born-Jordan distribution has a special importance in quantization theory, and especially that it was defined by Born and Jordan in the early 20s when they tried to characterize quantum mechanics, and they wanted to figure out the right quantization scheme for turning a classical polynomial in x and p into a quantum mechanical operator, which will then contain all sorts of orderings of powers of p and x because of the non-commutativity of the problem. And we characterized that the Born-Jordan parity operator looks like this. It still contains a coordinate reflection, but on top of that, it contains a weighted average of squeezing operators, where the squeezing operator just takes a wave function and compresses its arguments. And now this Born-Jordan contains all possible squeezings with a weight factor, which is similar to a Gaussian function. And we figured out that this Born-Jordan parity operator has no eigenvalues, which is interesting because in quantum optics, they typically use Wigner functions or S-parametrized functions. Their parity operators have eigenvalues, but this has a continuous, purely continuous spectrum in terms of these eigenvalues. Sorry, I meant it has no point spectrum, so no discrete eigenvalues. We then characterized how an approximation in terms of its matrix representation would look like, and we derived its matrix elements in the photon state basis, the so-called Fock state basis, which just corresponds to Hermite polynomials. And we could give a recursive formula for these matrix elements, which allow for a very efficient calculation of this Bond-Jordan parity operator. And on top of that, it can be approximated as a low-rank matrix. So it now really allows for efficiently calculating these types of plots and approximations of the actual function. And now here I compare the Wigner function of the 4-photon state. So a state of the electromagnetic field which contains 4 photons. It has these wriggles which are considered to be a sign of non-classicality or quantumness. And in the Bond-Jordan distribution, we see a quite different behavior in terms of symmetry and in terms of the number of wriggles. But if I decompose this into 2 functions, the sum of these 2 functions gives this, and this part corresponds to the diagonal of the parity operator, and these correspond to the off-diagonal terms in the parity operator. And the Wigner function is purely diagonal. So we see that there is a quite good agreement between the diagonal parts, and all the difference comes from these off-diagonal contributions. And now I will jump to the next topic, which is generalizing these ideas to finite-dimensional quantum systems. So the case when our density matrix corresponds or represents a qubit state or a qubit state. In that case, symmetries of the system are different. So here we have the so-called rotation operator or SU2 rotation operator, which is defined like this. But it is, in a sense, very, very similar to the previous case. What I just showed you is still an expectation value. It has the same structure, just taking into account the different symmetries of the quantum systems and having a different parity operator here. And we characterize these parity operators, and these lead to a continuous family of different representations, which include the Glauber P function, the Wigner function, and the Husimi Q function. Here I plot the W state of qubits, which is a permutationally invariant state. And it's a state that contains a single excitation. So one qubit is in spin-up state, and all the other qubits are spin-down state. And this contains all the possible permutations of this single excitation. It's also called a Dickey state. And then I plot different values of S for these phase-space representations. And as you can see, the Husimi Q function is still positive here, or non-negative. It contains no negative regions. And what we showed in this work is that if I increase the number of qubits, then it will cause the radius of the sphere to increase, but still the function itself is concentrated on the same surface area. And therefore, when increasing to the limiting case of j goes to infinity, we actually regain the single photon state from quantum optics. And there is a convergence to a state of the electromagnetic field in terms of the functions that I previously showed you. So there is a complete correspondence between the S-parameterized functions in finite dimensions and in infinite dimensions. And in these works, we were interested in how to calculating the time evolution of these functions for qubit and qubit states. And in particular, if the state is given in terms of a density matrix, then we just calculate a commutator between them, and this will give an infinitesimal step in terms of this so-called von Neumann equation. But we were interested in characterizing an analog of that in phase space so that it takes into account the non-commutativity of the problem, so that we have a phase space function that represents the Hamiltonian and a phase space function that represents the state itself. And then we need to calculate a commutator-like object which contains these so-called star products. And these star products need to be non-commutative because they need to be identical or analogous to Hilbert space product of operators. And therefore, these are actually differential operators on these smooth functions. And we, in the first paper, we characterized these star products for qubit systems. And in this paper, we generalized this to qubit systems, so for arbitrary finite-dimensional spin systems. And for that, we had to use so-called spin-weighted spherical harmonics, which is a technique proposed by Newman and Penrose, but in a very, very different context. This is how these functions look like. These are generalizations of spherical harmonics. And here we characterized both exact and approximate methods. And these approximate methods are very, very useful for calculating efficiently these phase-space functions or their time evolutions. So the star product, which I introduced earlier, is non-commutative and has this general form, which contains so-called spin-weight raising and lowering operators. These are differential operators. But I don't really want to discuss the details here. I will show you that we derived a very efficient approximation for finite-dimensional systems in terms of derivatives at the tangent plane of this sphere. And there is an approximation error which scales inversely with the dimension of the quantum system. And for j goes to infinity, we exactly recover the star product from quantum optics. So here we also see a convergence property. And this can be used for both calculating time evolutions approximately and efficiently, but also for estimating the phase-space functions themselves. And here is an example that I calculate some phase-space function exactly. It takes a long time because it's not easy to calculate these functions. And then I calculate it approximately, which is very fast, but it will lead to a quite strong deviation from the exact function. And as the system size grows, then the radius of the sphere becomes larger and larger, and we have a convergence to the plane, and we have a very good agreement between approximation and the exact functions. And the error scales with 1 over j. And for j goes to infinity, we exactly recover the state from quantum optics, or the corresponding state from quantum optics. And if you have any questions, please let me ask. I will also first thank our team from Oxford. With them, we carried out this work on quantum metrology. And at the Technical University of Munich, we worked on these phase-space representations. And also from Vienna, we have a collaboration with Professor Maurice de Gosson. And he wrote several books on many aspects of this phase-space quantization problem. And let me know if you have any questions. Oh, thanks.
So, any questions?
Thanks for this very nice talk. I'd like to ask about these different representations of quantum states on this phase space. Do you have any like physical motivation for any of these like beautiful extra functions? Like maybe results of some type of like measurements, like I don't know, homodyne, heterodyne, and so on and so on.
So, of course, one could just consider the Wigner function, which is typically the most convenient one. It has the best properties. This can be reconstructed in an experiment. We even describe this in one of the papers here. But it turns out there is a relevance for these S-parameterized functions as well. And in particular, the Q function can always be reconstructed just from the knowledge of the probability of the system being in the ground state. So in that sense, it's much more favorable than any of the others because it requires much less information to reconstruct the state. But then there's a disadvantage, of course, because it's a Gaussian convolved version of the Wigner function. So it's very hard to calculate back to the Wigner function or to calculate back to the density matrix. So it uniquely represents the density matrix, but then it's much more difficult to figure out which density matrix it represents. Another physical motivation for using these S-parameterized versions is that it has been shown that if one tries to reconstruct the Wigner function in an experiment, and let's say one uses a photon detector-based method for that, if the photon detector has less than 100% efficiency, so there is some photon loss, then one actually reconstructs a different S-parameterized version. And if the photon detection efficiency is 50%, then one reconstructs this function. And one cannot actually go for the Wigner function. If, let's say, the detection efficiency is 0%, which means all the photons are lost, then one reconstructs the Q function because it only requires the information about the ground state, so the zero photon case. Yeah.
Any other questions?
And maybe one more motivation. It's not physical, it's more like mathematical. But these Born-Jordan distributions are favorable when compared to the Wigner function in case of time frequency analysis, because then the Wigner function has obvious disadvantages, exactly these interference fringes. So this is another motivation. Okay, thank you very much, and I'll show you my last slide. Yeah, thank you for your attention.